So good evening to everyone. So welcome in this symposium. So ladies and gentlemen, estimated guests, welcome to a momentous occasion marking 6 decades of collaborating strides between India and France in the realm of space exploration. So hosted by Alliance Française de Jaipur, tonight's webinar stands as a tribute to this enduring partnership that has propelled our understanding of the cosmos. Though throughout these 60 years, the shared endeavors between our nations have not only elevated the exploration of space, but have also sparked innovation and throughout that continue to inspire us. So tonight we have the privilege of hosting two distinguished figures whose expertise and dedication have significantly contributed to this remarkable journey. Please join me in the welcoming of Alexis PAILLET, representing CNES, the French Space Agency, and Sylvestre MAURICE from IRAP. So welcome, Alexis. I hope you're well. How are you, Alexis?
I'm good, and thank you. Thank you to invite me for this symposium between France and India, and I'm very happy to speak about human and space exploration with you during the next maybe 1 hour or 45 minutes.
So yes, great. So yes, so you will start if you want. You can introduce yourself maybe and CNES activities, and after we will have 15 minutes of question and answers by our public. So you can start whenever you want.
Okay, so I will share my screen. So before starting, so let me know if you see correctly my slide. Oops, I will just change.
Okay, so this is the screen.
Yes, it's also a screen. It's in presentator mode, I think.
Yes, perfect now, perfect.
Okay, so I'm Alexis PAILLET from the French Space Agency. So I'm working on human exploration in spaceflight. Previously, before going to human spaceflight exploration, I was on several activities at CNES, like ChemCam with Sylvestre MAURICE, and you will have some slide from him, a talk from him in 1 hour. I was also in charge of the INT, so integration and test on other instruments like SACE, the seismometer on Mars. And I was also involved on the Saral Altica activity between France and India. I was in charge also of the integration and test on the payload we provide to the platform in India at ISRO to explore the ocean and see what kind of things could be done with the Nino effect on this, thanks to this satellite. So now I'm in the French. I have some activity around the exploration and human spaceflight. So what is the difference between exploration and human spaceflight? Exploration, we have two kinds of exploration. One is human, so you know maybe these astronauts. It's the French core team with 10 French astronauts. All of these guys go to the flight between 1 or 3 flights on the space shuttle, on ISS, and the last one we have is Thomas Pesquet. So Thomas Pesquet, I think you know him, and so it's the kind of things we do on exploration at CNES. And about the robotic activities, so we have some activity, and the main one is this one with ChemCam or SuperCam. And I don't want to go deeper on this one because I don't want to tease the activity done by Sylvestre after my talk. So what is the general context of the human spaceflight history? So we start with Yuri Gagarin in 1961. After in 1969, the first step on the moon by Neil Armstrong. In 1988, we have the International Space Construction start. it's a great collaboration between all the countries around the world in order to work around the space activity. And we expect the next step will be in 2040 with the human activity on Mars. And we are working together in order to do that. So in order to do that, we need to cooperate with all the countries. So, for example, on the ISS, we have some partners like US, Russia, Europe, with ESA, France, Italy, Spain, Canada, Japan. And for all the other activity, we have some collaboration between the National Space Agency and the others like China, India, Brazil, Emirates, and Korea. So we are working together because, in fact, if we like to go to the moon, if we like to go on Mars, we need to be stronger together because it's huge. The funding cost it's very huge, and of course we working together will help us to have to achieve this goal. So I have just an issue with Zoom. Okay. About the space industry. So currently, about the space industry around the world, we have Boeing, UCT with United Technology Corporation, Lockheed Martin in US, in Europe, with Airbus, British Aerospace, Thales Alenia Space, and Arianespace. And of course, there is a new kind of space actors are very dynamic on the sector. So it's the new space, like SpaceX, Blue Origin, Virgin Galactic, Axiom Space, and some small company like Spartan Space in France. But a lot of company are working on these sectors in order to go to space. So it's a very dynamic sectors. About the space organization, okay, so we have the European Space Agency, we have the European Commission, and we have some national agency like the CNES, the French national one, the DLR, the German one, ASI, the Italian one, and some others are partners at ESA to achieve this goal to reach the Europe and Space Organization. We have some partners, some research partners, like IRAP, also with the space industry and academic. So we are working also with all these partners to build some equipment, scientific equipment for Europe. Okay, so so it's not very. Just a few words about the active European astronaut we have. So we have 6 active astronauts currently. So one woman with Samantha Cristoforetti from Italy, and 2 and others are male, like Alexander, Andreas, Luca, Thomas, and Matthias. All are going to the ISS 2 times. And we select the new class of astronauts. So this activity starts in 2020, and during these 2 years we select our astronauts. So 22,000 candidates, 24 women, and 200 candidates for the on-the astronauts. And at the end, you have a core team of several astronauts, and we have 2 astronauts like Sophie, I don't know, active one, and Arnaud go to the reserve. Okay, so what is the life on the ISS? So I start my talk previously in 1988. So we start with the ISS in order to build together this ISS with the Zarya module, the Russian one, and we have some others module are coming to create the ISS from 1988 to 2011. So you will see some several change on the International Space Station. And with the 5 agencies we have, so NASA, Roscosmos, ESA, JAXA, and Canadian Space Agency, we build this huge international space station. Going well. Okay, so if you look at the ISS, in fact, it's 2 parts. One is Russian, and the other part is more international. About the international one, 75% is US, and others. We have 10% from JAXA, 10% from ESA, and few percent for Canada. And all of these, if you look carefully, you have the selection of and the core we have inside the ISS. So all the time there is 3 astronauts from Russia, and the other. So the 4 astronauts are from US, Europe, JAXA, and other agency. So you have the color of the ISS thanks to this color, because between agency we don't have any exchange funding. It's only barters. So if you give something, if you give a technology, you could have sometimes to the ISS. And it's a reason why we have sometimes French astronaut and sometimes others. It's just because we just reach the cap to the value to have an astronaut on the ISS. So if you look the ISS now, roughly it's this one. So in few numbers, the dimension and the volume of the ISS, it's like a big airplane. So 100 meter long, 73 meter wide. The volume inside it's quite big enough for seven people, because you have more than sometimes you have on your apartment. If you look the metallic structure weight, it's roughly 400 tons. About the altitude, it's between 360 to 460 kilometers, and about the traveling speed, it's 27 or 28,000 kilometers per hour. And the sunrise, so we have the chance. We are lucky when we are on the ISS, because it's 16 sunrise per day, so it's not so bad. And about the line computer, approximately it's 1.5 million. So and sometimes we have some issue when we need to download and upload the code in order to stay on the right place. If we look now the ISS control center, there is 5 control centers around the world. One is in Houston, the second one is in Unville. So these 2 parts, one is for the payload, and the others it's for the instrument inside the ISS. There is one for Moscow for Russian module. The 4th one is in Tsukuba in Japan, and the last one is in Munich in Germany for the European activities. And one of the European activities is performed in Toulouse in order to check some European payload inside the ISS and the Columbus module. Why is important to have ISS? So ISS is a science laboratory, because inside the ISS we are not able to perform. We are able, to perform the activity we are not able to perform on the Earth. So on the chart you have on your left, you have some activity performed by inside the ISS, so biology, Earth and space science, educational activity, human research, so psychology, psychological science, and also technological demonstration to inside the ISS, thanks to the microgravity we have inside. So it's a lab. It's a lab, and thanks to this lab, we are eternally on microgravity. So we have some constraints, so the mass, the volume, the radiation, the temperature, the microgravity, the safety for toxicity restriction. So we have some people inside are working for your activity. So we need to schedule everything on the ISS, and the major part of the time we have on the Earth, on the ground segment, is to perform the schedule on the ISS. The microgravity is important to test a lot of things. The most important thing is the physiology inside the ISS in order to test the activities. For example, the effect on the body, on the bones. For example, on the ISS, if you stay 6 months on the ISS, on the ground, it's like you perform 10 years. So, and when you come back, of course, it's reversible. So thanks to that, we are able to check a lot of things on the body to know what kind of things could be done on your body during the next year, and it's important for that. What is a typical day in the ISS? So okay, on the morning it's the wake up. We have some inspection, a general conference to the ground in order to check if everything is okay and correct for the day. And after we do some science experiment or station maintenance. They try to lunch together at noon. And on the afternoon, it's also a scientific experiment and station maintenance. There is some physical activities, 2 hours per day, and at the end of the day, there is a call or conf call to the ground in order to prepare the next day or the next activity, and astronauts are maybe the issue they have or others. After it's free time, dinners, and it's time to sleep. But what we are doing during the weekend, in fact, during the weekend, they're supposed to clean the station. They could take some rest also, because for the guys are going to the ISS, stay 6 months on the ISS, 6 months to 1 year. And in fact, for mental activity, it's important also to stay a long time on the ISS. We don't want to have an issue and come back one astronaut from the ISS to the Earth, because it could cost a lot of money. So they are working all the week, and the weekend they can redo some activity. We can redo some science tests, but they could take some rest as you want. What is also a typical schedule inside the ISS? So this kind of schedule. So you have a commander, you have some guys on the ISS, and all the block you see is to perform an activity. So as you see, it's very tight, and it's just because we don't want we would like to also to stress a bit our astronauts in order to stay awake, to stay focused on the activity, and to be sure they are performing the task. So they are doing also some physical tests, like running, like a raid, and also bicycle. The daily life, so crew quarters, they're sleeping, they're moving, they're eating, there are some hygiene, there is some toilets, they need also to clean. So of course, it's very important it's like at home. In fact, you need to it's a daily life on the ISS. About the EVA, so the extravehicular activity. So it's very important to have this kind of activity in order to repair, for maintenance, for MCO, the control and the assembly, to maintain the ISS on the right place on the orbit. So there is some training to prepare that. There is some preparation, because in fact an EVA, it's 8 hours task. So it's very stressful for this activity, and all the people are focused on that. So they need to adapt to the extreme environment in order to prepare the activity we would like to do on Mars and maybe on the Moon. So for us, it's a technical and human challenge for the life support system to prepare and to stay sustainable and also autonomous for on the life system in order to also to prepare the psychology, the physiological activity, and the effect on the radiation of the body. About the exploration and robotic and human spaceflight activities. So as you see, we have the ISS, so it's very close to the Earth at 400 kilometers. Thanks to the human exploration, we go to the Moon with US a few years ago. And of course, all the other things are all have been discovered or studied by probes or rover or lander on the solar system. So we have a well knowledge of the solar system. But the most important things is to go to see with rover, but go to see with human. It could be also interesting. That's why it's a goal also for the human and exploration to go with human on Mars in order to study this planet in order to have a better knowledge. What is our programmatic context? Today, the Moon is the major destination for all the international exploration. So they start with US, then China, and Europe with the Terra Novae program. There is some other contributors like Korea, India, and other countries are going to go to the Moon. Our goal at the French Space Agency is to have a French scientific community and to benefit with many potential opportunity for the mission to the Moon, to have also and to prepare Mars and beyond. So how the French actor could develop this lunar activity and make up, yes, a scientific community between technology, industrial and scientific. What land-based contribute to expect and research for this kind of cooperation? It's some question we try to answer on this programmatic context and preparing our activities. So there is some new actors, like I talked previously with Axiom, Orbital Reef, Thales Space Rider, the exploration company, Spartan Space, Ice Cubes. So we have a lot of companies are working on this topic. If you are looking the launch manifest provided by NASA, so the idea is to go on the Moon with the following activities. So they already start in 2022 with Artemis 1. So we go around the Moon automatically without any astronaut inside. For the next activity, supposed to be in 2024, but maybe you could slip a bit on 2025 with Artemis 2. There is a crew inside the Orion module. They go around the Moon and come back and don't touch the Moon. But for Artemis 3, we are supposed to have some EVA activity on the ground in order to keep some sample and to bring back some sample from the Moon. So it will be in 2025, and after we are Artemis 5, 4, 5, 6, 7, and others in order to prepare the exploration around the South Pole of the Moon. There is also the Gateway. The Gateway, it's like the ISS, but it's a station not around the Earth, but around the Moon. This one will be automatic, and maybe few days or few weeks by year. This one, some astronaut will go inside before going to the Moon. So here you have the activity on the path to the lunar surface. So they start with few people and few module, maybe some shelter to extend the exploration, and maybe after we will have a permanent lunar base on the Moon in order to prepare our goal, and the goal is going to Mars. So here you have the step-by-step by Artemis 1. So it was a successful mission with the crew. So before going to the moon, we need to have some input. We need to have some data from the radiation we will have. So that's why during the first mission, there is a lot of sensor inside the module in order to know what will be the radiation. So in order to protect our astronaut when he will go to the moon. The next step, okay, is going on the ground and to prepare an Artemis base camp to explore and to perform some ISRU, so some in situ research utilization to bring back some rocks, some samples from the moon. So here you have the American and the US program. Of course, Chinese have also a program, and the goal to Chinese is to have two taikonaut, two astronauts on the moon surface in 2029. So it will be the 90th anniversary of the Republic of China. In order to do that, there is a very strong program starting with Kikao 2 to Chang'e 8, in order to have some landers, some rovers on the South Pole, and they are preparing the activity for to have two taikonaut, two astronauts on the moon with several launchers. And there is also the ILRS, so International Lunar Research Station. So it's the Chinese and Russian program working together to go on the moon. So it's this one. Of course, in Europe, we have a program. It's Terra Novae on the moon. So with several contributions to other countries. Currently, we're more working with Artemis program to provide moonlight. So it's kind of constellation around the moon. Argonaut, it's a lander. Esprit and IRAP, it's a contribution to the gateway. A contribution also like a service module to Orion. So the Artemis with the astronaut. See, it's all the contribution we have currently with US people, with Artemis, to prepare also Europe on the moon. So the goal is, it's an ambition to Europe. It's to have the first European on the moon before 2030, but we will see if it's feasible, doable during the technical constraint we have all together. Okay, so going to the moon, so it's not so easy. So we start with the LEO, so the low Earth orbit and moon and Mars. So it's kind of we need to multiply by 1,000 each time. So we start at 400 kilometers, 400,000 kilometers is the moon, and 4 million kilometers roughly it's Mars. So it's not so easy. But what is our future for the human space flight? Currently, the ISS is qualified until 2030. Is moving to a public company to a private co-management. After we have the lunar gateway, some lunar habitats, and maybe a permanent moon base on the moon. So what we want to do on the moon, we want to do some scientific exploration in order to explore the moon. So what we want to do from the moon, so it's more difficult because as we have a new space, we need to organize a kind of a circle between agency and emerging actors to coordinate what kind of activity could be done on the moon in order to protect also the moon. If we look at the Artemis architecture segment, so we start with a human lander return. We have also some fundamental exploration, sustainable lunar evolution in order to prepare the human to Mars. for the space resources utilization, the synergy we will have is a synergy between space and terrestrial needs for working on food, waters, construction, energy, and mining. If we look at the food and water, so improve the water cleanup technically, because in fact, if we would like to go to the moon, we need to reduce also the frequency cargo between Earth and our goal. For example, on the ISS, each month or each 1 month and a half, there is a rocket going from the Earth to the ISS in order to give some food, to give to have some fresh air, water, and others. But if we go on the moon, it's not possible to do that each month. So each 6 months could be a good option. So we need to improve our water cleanup. We need to advance our food, the technique of production. For example, also for the construction, so we need to elaborate some new material. We need to use some 3D printer. For the energy, we need to be more efficient of power generation, storage, and distribution. And also reduce our carbon dioxide emission. And for mining, so it's in order to reduce our maintenance and logistics and increase the mining and process efficiency. The idea is to promote and reduce, reuse, recycle, repair, reclaiming for benefit in order to be more autonomous. As soon as we have autonomous activity, of course, we can think to go to Mars. For the space perspective and long-range view, so thanks to the ISR, we can reduce our mission, our architecture, mass, and cost. We can also increase our safety for the crew member, for the mission, and allow us to explore further from the Earth and from the moon and beyond. Learning by using the space resources could help Earth. And also a planetary preservation is more important and has possibility to use our space resources. So what we would like to do at CNES is to preserve, use, and understand on the activity we will do on the moon by simulated, gather, and inspire. So simulated with startups built from the Earth to the moon, a sustainable economy based on the innovation. So we need to do that together, so scientists and also industrial, and preserve and use, so inspired to national organization to prepare the sustainable use to preserve also the Earth. So if we would like now to go on Mars, we need to prepare our suitcase. So going to Mars, it's not so easy. So we have some cargo, we have some rockets and a lot of rockets, and we need also to prepare the Mars transfer vehicle between the Earth to the moon, to Mars, sorry. And also, if we bring some astronauts to Mars, they're supposed to come back. So we need to prepare also the comeback from the astronaut to Mars to the Earth. So it's a big challenge. There is a lot of remaining to do that, instead of radiation, psychology, physiology, communication delay, autonomy, and life support system. So how to stay alive in this artificial environment? So we need to have some air, some waters, some food, some to treat also our waste. For example, on the Earth, okay, it's this kind of composition, and if we decrease some parameters, we could. It's not human can survive, but we need to stay in this kind of composition and pressure to stay alive on this artificial environment. On the water, also we need some water to stay alive. In France, so the average water is 150 liters per person per day. Of course, it's not possible to have this kind of consumption if we go on Mars. So we need to recycling to have a recovery of the water in order to only live with a few liters per day per person during the traveling. So what is our human needs and other consideration? So the very important is the psychological needs and safety needs. This one is vital for life in space. So it's a specific space habitat system. So how we can design this artificial environment. So we have a crew, we have our goal, so it's Mars, we have the distance, and we have some key driver like some stakeholders, the crew side, the mission duration, the launch, the reality, the size of the habitat, the type of, so we have a lot of observable to organize that. So it's possible to use, and we need to use the space resources. So all our waste will be our resources if we are going to Mars. So we need to create this kind of closed loop to prepare our exploration. So what is the future deep space human exploration? The mission to Mars, it's stressful. So the day, the most short day, it's 500 days, but the long stay, so it could be close to 900 days, so 3 years, to go on Mars and come back and do activities also on Mars in order to have the right configuration to come back. What kind of environment we need to have? So previously, for example, on the space shuttle on the ISS, it's a kind of open loop for the environmental control of life support system. So I already say all the months, sorry, some rockets are going from the Earth to this module to supply, to refurbish activities and feeds need for our astronauts. But if we are going to Mars, of course, we need to close all the loops for the environmental life support system. So everything will be recycling in order to have a lower reliability, to a low resupply requirement and high resources consumption. For example, the power, the thermal, and water, and all the needs we need to have when we go on this outpost. About habitation system element, today, currently on the ISS, we have this recovery. So it's 42% of O2 from the CO2. It's 92% of HO2 recovery. If we would like to go on a future deep space, so Moon or Mars, we need to increase everything. So increase everything maybe to reach the 100% for the water recovery, and for the air, for the oxygen, we need to increase our recovery, and also we need to use the resources we will have on Mars. For example, there is some technological demonstration like a MOXIE on Perseverance rover. We take some CO2 from the atmosphere and give some O2 in order to prepare this kind of activity for the following decade. So everything needs to be increased. So it's good for us to develop some technological demonstration in the future. So how your suitcase? So we need to work on the recycling, decrease the number of the water bottles, working on the oxygen, working also on plant, how to grow it, how to develop our plant. We need to be on a circular loop, a closed loop activity. So how your waste will be your resources. We need also to work on your clothes, because it's not possible during 3 years to take all your clothes you are supposed to use. So we need to reuse it or take some techniques to recycle this clothes. And also there is a huge part of digital to help our astronaut, because it will be a crew of 6 people, more, or maybe less. But in fact, with the 6, even if they are very smart, 6 people is not enough. So digital will be everywhere. Intelligence artificial will be everywhere also, to help astronauts to take some decision, to help our astronaut, because due to the delay we have between Earth and the Moon, the time delay is 20 minutes to go to the Mars and 20 minutes to go back. So it's not possible to perform a kind of conversation together. Everything will be autonomous. So we have a ground segment today, a ground segment on the Earth. So behind one astronaut, it's 400 people on the Earth. So it's not possible to take these 400 people and go to Mars to help our astronaut for housekeeping, voltage, temperature, acquisition, and others. So this ground segment will be also in situ. So how the main part of our goal now is to prepare this ground segment who is on the Earth, is working well, and prepare it to go on the Moon and Mars. So in order to do that, at CNES we have a network, and this network is a spaceship. So we're working on all these activities in order to prepare the activity on the Moon and beyond. So the spaceship, it's a network of 3 spaceships. We have a 3 spaceships around Europe. Was in at ESC, at European Astronaut Center in Cologne in Germany. The second one is at EXAT in UK, and the last one is in Toulouse. All of these spaceships are working together to prepare human spaceflight and exploration activities, analog support. There is also developing R&D activity with commercial partners. We have under one program at ESA, call it Expert, for exploration, research and technology. So we are working on a very low technological readiness level to prepare this activity. So prepare some demonstration with an innovative team to select some partners, maybe new startup or new people are working also on this activity, because previously it was only space people, but now as we are open the door to go to Moon and Mars, of course, there is some technological domain. We have some very smart company on Earth, and it's not space, but we use this company and we push to space thanks to the space agency. So we are working on several thematic areas in order to bring some French technology to the Moon and Mars. So we are integrated in a European program, and we have some synergy between all European contributors. We have also some synergy and partnership between international projects. So it's a B2B. Like also we have some barters between national agency, so between the CNES one, NASA, the CNES, and the Indian, the ISRO, in order to provide some technology. But we need to select our technology, so it's not so easy, because in fact we have a limited funding. So we need to select the right one. In order to do that, there is a coordination group. His name is ISECG. The ISECG is the International Space Exploration Coordination Group. Is working. It's 26 nations around the world. Sorry, are working on the global exploration roadmap. And define how to reach our goal to go to Mars and the Moon. After, okay, so it's the top-down approach, and we have also the bottom-up approach. So we need to look how our French ecosystem, and thanks to that, we select thanks to the bottom-up and the top-down approach, we select the French technology in order to say, okay, we could go on these technological bricks to prepare the exploration. And at the end, France will bring some technological breaks, other country brings some other technological breaks, and all together we will build this outpost, this international outpost to explore Moon, Mars, and others. So what is our capstone? The capstone at CNES are the following. So the first one is an autonomous habitat. So we call it LISE for Lunar Integrated Shelter for Exploration. This one will be land on the moon without any people inside, but thanks to this autonomous habitat, we could extend the exploration. So it's a kind of shelter when you go outside. So thanks to this shelter, there is some food, water, fresh air inside, and you could extend this exploration around the south pole of the moon. Also, there is another one is the robotic assistance. His name is Laura for robotic operation. Lunar operation with robotic assistance to help our astronaut to have some toolbox and to help astronaut in any circumstances with autonomous navigation, follow me activities, scoutism, and others. There is also a prospective tools because, as you will know in few minutes, thanks to Sylvestre, we have in France we have a good science community around optical geology. So working on this kind of prospective tools could help and could be also a good barter between all the nations to explore the moon. Thanks to that, we could do ISRO, to the Institut Resource Utilization, and we will use digital and supervision for these autonomous habitats and prepare the next outpost and prepare also the food management and the infirmary. So it's, I think I'm close to the end, Alexandre. It's how many minutes I have?
Yeah, yes. Maybe you weren't finished. You have something to add because the audience has got some questions for you.
Okay, so I will go quickly. I have maybe in 5 minutes. I will finish it. The main part. So the lunar integrated shelter for the exploration, to prepare the life support, the habitat protection. We have some main requirements. It's 2 astronauts inside, several consecutive days. This one needs to be reusable. We need to reuse it. Frequency, the frequency to reuse it is each 28 days. So each moon, it's clocked with the moon. Autonomous deployment and some activity. Thanks to that, we could be able to develop all these activities: the life support, the inflatable frame, the radio protection, life support for astronauts, the energy valorization with RFCS, so regenerative fuel cell with hydrogen or iron battery. The digital twin also for AI, so artificial intelligence for a planetary outpost, and activities we could propose to the main shelter. It's my last slide. So thanks to all the activity we will have, of course it's too tiny, but the main important thing is the title. So it's a spin-off for industrial, academics, and laboratory. So thanks to the space exploration, we can use it like a vector to propose some technology, some terrestrial activity, and push to the challenge we have on space in order to develop and to miniaturize, to develop some to increase this technology, and this one will be beneficial for the Earth. And because in fact what we need is to have a sustainable development thanks to this exploration. So thank you everyone, and I will be happy to answer to your question.
Okay, thank you so much, Alexis. So yes, we have some questions, but first, can you tell us a word about the India and the French collaboration about this project?
So we have several collaboration with India. The first one is on the ISS. We provide some device, some equipment to India. We also prepare some Indian astronauts to go to ISS or to go to another station. Now it's open. And yes, we provide some device like ultrascan, echography to promote also the cooperation we will have between France and India on the exploration. For the science, maybe Sylvestre have a better answer than me, but for the others, like Earth observation, there is a strong cooperation between France and India. As I already say, I work on Megatropic previously, also on Saral. So all these contributions are very important for us, for the climate, to prepare the activity together. So
okay, thank you. Alors, we have a question of someone. How much does the main goal of ESA and NASA differ? And like, what are the main goals of these two agencies? So, to sum up, what is the difference between ESA and NASA?
It's very different. In fact, ESA, it's a cooperation between national agencies in Europe. So in Europe, you have several agencies because it's several countries. And thanks to that, all these national agencies give some money in order to be stronger and bigger to ESA. So, for example, I give €1 to ESA, and this euro to ESA is money back to France after. But thanks to this euro, so for example, France give €1, Italy, Germany give some euro. It's we will have more money and we could start a big project, but the contribution after need a geographic return to the country give the money first. So it's a ESA context. At NASA it's different because NASA it's big, it's huge, and all the states are together. So if there is no this kind of competition inside to have the money back and to say, okay, I'm able to perform this device because I'm blah, blah, blah. The main difference is this one between ESA and NASA. But at the end, ESA gives the money, but they give the money because also the national agency at the beginning say, okay, I want the money back thanks to this vector because so each 3 years we have a kind of ministerial, and during this ministerial, all the money we put on the table, we say, okay, I want some percent in France, some percent for this activity, Earth, launch operation, space exploration, and others.
Okay, thank you very much. So we have a second question. So what is the full form of ISRU?
What is the
full form?
Full form. It's true. It's quite difficult to explain because it take several topics. The main one is to don't bring back things from the Earth and use all the material we have on the place we plan to go. So if, for example, if I go to the moon, the only thing I will find is the sun and the ground. The ground is regolite, so it's a kind of powder. And thanks to this powder, if I can use it very well, I could extract iron, aluminium, silicium, and other things. Inside also, on the moon, there is some some ice. So we could take the ice and give some water, use it in situ. So on the place I plan to go. And after, on the ISRU, you have also organic and non-organic activity. So about organic, it's all the waste I will provide, like a human, like a plant, and reuse it, and reuse it again. So this one is the space resources we have. So all the waste we have will be our resources in order to decrease the frequency between Earth and the Moon to increase autonomy.
Okay, so we have also a question about Artemis 2. So how much money will Artemis 2 be worth?
I don't know.
Okay, simple answer. So next question. What is the way to be an astronaut? And if anybody has specs, can he or she be an astronaut?
Okay, so maybe depend of the country where you are. But just to say something about Europe, in Europe, the starting process, the process takes roughly 2 years. So you start to apply, so it's good. It's not so difficult. After, you need to have also you have some psychological test to perform. It's on just behind your computer, and you do what is supposed to do. So, for example, I give you a list of number, and I say 1, 2, 10, 6. Give me the number I say a few times ago. So it's this kind of things. So it's a first selection. After you have some over selection. To be sure you could work with other people. So few candidates arrive in the room. You have some, and you have a topic, and you need to solve this topic together. So they look at it if somebody takes the lead or not. These kind of things, and at the end, because it's more cost constraint, you have the medical test to say, okay, I could be active or not. So roughly is this kind of things.
Okay. Alors, how many years was ISS was built? In how many years?
They start in 1998. They keep maybe until 2011, so 30 years.
Okay. So I've got a question from Taha Hussein. So there is a new circuiting around that NASA is planning to deorbit the ISS in the year 2030. So is there any particular reason for it? Like won't letting $1 billion station burn up in the atmosphere too wasteful? Like can they keep in the orbit?
Currently, it's not so clear. They plan to put the ISS on the sea. They try to push as far as they can. So it's not really the plan.
Okay.
So because each 5 years they say I postpone to 5 years, so it's we need to wait.
Okay, great. Allez, maybe you can just a quick word about maybe before let the speech to Sylvestre Maurice. What about UFO? So they exist or they don't? Aliens.
They
exist or they don't?
UFO, from my point of view, I think we are not alone on the universe, but maybe it's not like you, maybe it's not like me. Of course, I'm pretty sure, okay, the life take a path, and it's like that with us, but on another planet, on another solar system, it's there is some other things, some other intelligence. So I'm not sure it's UFO, but it's something intelligent to yes to be on the planet. Maybe Sylvestre, you have a better answer than me.
Yeah. So yes, we have a question about Mars missions, but maybe we will let now speak the specialist of this question. So thank you very much, Alexis, for joining us tonight, and we wish you good luck in the CNES to have a lot of future success.
Thank you.
Thank you very much. Thank you, Alexis.